Okay, so hey everyone again, and let's start. So I'm going to start with showing the basic diagram of the structure of OpenEthereum, like how it's structured. Some of you may have already seen it, but I think most of those who have joined us just now have not. So this is OpenEthereum, like the basic overview of how it's structured. I'm going to give it from the bottom up rundown, starting from the most bottom layer upon everything which stands. This would be the dev P2P. So as you know, the dev P2P is the networking protocol used by various Ethereum nodes to connect to each other and to talk to each other. So this is, and it is not necessarily about blockchain, it's just about any data which can be transmitted in a P2P fashion. So, and as you see, it's as simple as read packet and write packet. So this is like a very basic abstraction upon which you can build blockchain, or upon which you can build Whisper, for example, or another protocol like LightNet protocol, but we'll come to those later. Upon dev P2P rests the sync, and the sync is about syncing the blockchain itself. So it fetches blocks, it fetches block headers from other peers. And here we have this small thing, it's called node filter. This is one of those things whose future is to be actually decided, but for now, this is something which is used by OpenEthereum to determine if we can connect to the peer, because some private networks may use the smart contract, which can be deployed, and in which the node ID, which is here, may be whitelisted. So basically this forms like a filter, a smart contract based filter for connecting to other peers. Upon sync, we have the various IO workers, which is like one giant pipe which connects other parts of OpenEthereum to each other. So going from there, we have verification, which verifies incoming blocks and feeds them into the client. Also, we have the engine. Engine is basically a trait which represents a consensus engine. And we can here plug in different engines, like, for example, ET-hash, authority round, instant seal engine, which can be used for instantly sealing blocks, which is useful for private development chains, and so on. Also here we have the so-called machine. We'll come to it when we will explore the code, but basically this is an Ethereum-like state machine. Here we have the basic client. Here we have WASM and EVM. Basically, these are different virtual machines, and which can read EVM contracts and WASM contracts. Also, we have here the snapshot service, which is responsible for the warp sync, taking the snapshots and serving them. Also, the miner part, which is still present and still useful for OpenEthereum. And also some of the additional features of OpenEthereum, like the exclusives, like private transactions, secret store, and the updater. These updater based on the smart contracts, which allows automatically deploying it to OpenEthereum installations. IPFS API used to be a feature, but it has been cut recently before the diagram was, after the diagram was created. So let us dig more deeply into the code. Basically, this is the OpenEthereum codebase. It consists of approximately 190,000 lines of code. I counted this just today. Even if we exclude like license headers, for example, it will still be like a huge amount, very close to that number. This is a Rust code base, well, as you can see, and it is split into multiple crates, which are, you know, libraries in the Rust language. So as far as I remember, there are around 60-ish, I think, crates. But I may be wrong here, but the ballpark is approximately like that. And it is split into various directories, basically one directory per crate. And some of these are maybe nested, but we will go over that. So I think we can start with accounts. This is related to the account management. There should be no confusion in that accounts may mean slightly different things, because accounts in Ethereum, like in Ethereum virtual machine, are different from the accounts here. Here it's about key management, private key management. So this is slightly different. And basically we have the OpenEthereum, the keys generator, and the key management. This is something that is, you know, like a bit extra to the full node. So not necessarily, this will not necessarily stay in OpenEthereum. So if you would like the account management to stay, I encourage everyone to join our tomorrow's call to discuss this and to voice your support or opposition for this. And I'm going to more thoroughly cover the full node stuff. So this is going forward. This is the chain spec, the OpenEthereum chain specification. Yeah, this is another binary which allows checking if the chain spec is valid, and if it's not valid, then why. So this is a very thin binary which uses internal ETH-JSON machinery, which we will cover later on. Then we have the CLI signer tool, but this is about the signing and private key storage, which I'm not going to cover extensively. So this is the ET-hash crate, and this contains the ET-hash implementation, as you can see. Going forward is the ETH core. ETH core is actually a very large collection of various crates. It used to be a single giant library, and there is still this crate, but it has mostly been split up into this. So AccountDB, basically like database, a backend wrapper for the account try. So yeah, it contains the various accounts, as in Ethereum accounts, and the data structure, how they are basically stored in the database. I will be honest, I haven't dug into all of the account database stuff yet. So if I'm wrong at some points, David will correct me, I think.
I have
So
in it, and it's I'm still unclear on what the exact difference between account DB and account state is. There's also executive state, that is a somewhat artificial split of pieces of code that have interdependencies that made them convenient to split out this way, but might not be super obvious logically why that would be. Both account DB, account state, and executive state are essentially the infrastructure that is needed to execute transactions and operate on accounts and their balances and or their code. So they are definitely very, very core crates, all three of them, and they are quite tricky to follow. So yeah, it's a challenge.
yeah, I mean, 190,000 lines of code, and some of it may be obscure, even if it is the most vital one, like account storage. So yeah, these are all three crates and all interconnected and not yet clear to some of us. So this benches. So I think this is just a set of benchmarks of criterion-based benchmarks. Criterion is a Rust benchmark framework, and these benches are based on it. So you can run it on your own time if you want, but not super interesting. Block gas limit. So this is the block gas limit contract, which is used in Authority in Aura engine, and as far as I understood, it allows. I'm not even sure what it allows because I just started reading it up on it today, and Dave, do you know what it is actually?
Sorry, where are we? I was looking at something else. Block gas limit?
The block gas limit.
Right. So the background to this crate is a refactoring that allows proof of authority networks to keep some blocks a lot smaller than normal blocks so that they can push in, so that there's space in the block for transactions that they need for consensus administration, essentially. One example is a contract that regulates the set of validators, and sometimes these validators are recycled, or new ones, you need to change the validators, simply put. And so once a week they run sort of administrative tasks to see which validators should get what awards and what the new ones should be, and this all takes place as transactions in a block. And if the block is full of other transactions, these transactions may not have, there's no room for them, and so they're pushed off, and that causes all kinds of problems. And so what they introduced was a way to sort of say that this block here has a gas limit of X instead of Y, and so now they have more space for these system transactions in those blocks. So it's code that it's logic that lets the gas limit be decided by a contract.
So basically a reserve seed for like the necessary transactions to run the POA network.
Yeah, correct.
Yeah. Thank you. So next is the block reward. This is also a contract of the POA, And this is about giving the block reward not to a validator, but to a contract. At least as far as I understood it, yeah, it works like this, and it was implemented for this. Blockchain. So this is the blockchain database, test generator configuration, caching, importing blocks, and block information. So forewarning, for many crates, even if they're big, it is always useful to look at libres and see what the crate exports. This is true for just about every ETH core crate around here. So like if you have a very large crate, just take a look at libres and see what it exports. And you will quickly get the idea of what the crate is about. So in this case, the crate is about most of all the blockchain. Basically, the structure providing fast access to blockchain data. So basically, this is like, I think it's like a view, and it contains various caches. Yeah, and along with access to various data behind the mutex. So also in the blockchain we have block receipts, but no, this is Ethcore DB. From this crate, it's just blockchain and blockchain DB, which is trade backing the blockchain. So provides access to key value, blooms, trace blooms, and restore. Okay, built-in. So this is the VM built-in. It provides the, as for the namesake, the VM built-ins. So yeah, the pricing scheme, execution definition, and activation block for a built-in contract. And also the cost to compute the cost for the given input.
Yeah, in Get is called precompiles.
Yeah. Yes. Exactly.
I think all of Ethereum call them precompiles. Even we call them precompiles, except the crate is named built-ins.
Yeah.
Maybe that's a great first task to rename that. I don't know.
Maybe. Just to follow the common nomenclature, the principle of the least surprise. Contract, call contract. Now this is another type of the crates, like the call contract, and we will experience more of them. So this crate consists of a single trait with a single method. But yeah, it was still better than when there was a single ETH core crate. As far as I understand, it was this way before, but it's been separated and into like various degrees of granularity. So I think we will encounter one or even more crates which just have one trait and that's it. So basically this is a trait which represents any entity upon which a contract can be called. So that's it. Client traits. So basically, client traits is trait definitions relative to the Ethereum client, but what it actually means is this. The blockchain client trait, which is basically an entity, which represents an entity that owns and manages a blockchain and a block queue. So, this entity, as you can see, it also has a lot of trade bounds, and basically it inherits from these trades from all of them. So anything that wants to implement blockchain clients also has to implement these more granular trades. Why the granularity? This granularity allows for like very easy testing. For example, if you want to test just the account data behavior, or let us go to the simpler example, the call contract, which we have just seen, you can just implement the call contract in your test fixture and then use it for unit tests. So this granularity is very useful for testing OpenEthereum, and there is extensive testing machinery around here, but we're not going to focus on it too much. So basically, this is a trait with a set of accessors which provides a view into the internal structures of a blockchain client, basically. So like an accessor to get the current block hash, or to get a reference to the block provider, which basically can tell you what the best ancient block is, to get the raw block data, and so on and so forth. So basically a set of behaviors that each full client implementation should implement. DB. So this is the DB access utilities, and basically this is so again, this is about traits, and these are the traits used for gluing various DB implementations, basically, like KVDB or a simple in-memory hash map, like we can see here. Like, but in case of hash map, it's a cache, and in case of KVDB, it's readable. So it allows us to just plug in another DB implementation, not just parity KVDB. Engine. So engine describes the consensus engine, the engines which are in OpenEthereum. As you know, OpenEthereum has multiple consensus engines, and the engine trait, which we can find right here, is what unifies them and allows plugging them in. And it describes the common behaviors, like what happens on new block, on closing block, on seal block, like how we should attempt to seal the block internally, and so on and so forth. Like, there are a lot of methods here. So if when you are working on the consensus engine, you can take a look at all of them. And and we also naturally export anything necessary also for the consensus engines definitions, like a system call enclosure and so on and so forth. So I'm not going to cover this in great detail right now. Engines. So this is the set of various consensus engines that are present in OpenEthereum, starting with authority round. So this is non-instant BFT proof of authority engine. It's like we can see, yeah, so we have the authority round engine structure here, and it implements the engine trait here. So basic authority, basic POA blockchain engine. Then we have click. Then we have ET hash, instant seal, which is useful for the development. Null engine, this is for testing, for internal testing mostly, and validator set. So basically, all of these engines have like a very common structure in that they all implement engine. So I'm not going to cover them in great detail because architecturally in OpenEthereum they're almost like plugins. Well, they're not plugins, but they implement the same trait and they can be switched at runtime. So they're more or less architecturally similar. EVM. So this is the Ethereum virtual machine Rust implementation, and what it provides is basically the set of instructions is here. So these are all EVM instructions which are present. This is the metadata of each EVM instruction. So the basic description, instruction info. So the EVM factor, which creates the appropriate virtual machine based on action params and schedule. So the schedule is the basic description of how each instance of virtual machine created using the schedule should operate. Basically, if it has the necessary instructions listed in the engine, and if and the gas price for each operation. So going back, so yeah. So, and the factor provides us with the fresh instance of the VM, and this is in this case it's in opaque object, and that it just implements exec, and exec means just execute a transaction, and then the result of the transaction execution. WASM. So this is like EVM, but except it's WASM. So WebAssembly interpreter. So basically we have WASM interpreter that also implements VM exec. And just to be clear, exec is not in EVM, but in VM. So it's another crate. Okay, EVM bin. So this is the like EVM, but wrapped into a binary. Okay, do you guys hear me?
Yes.
Ah, okay.
Yep, no problem.
Yep, yeah,
Yes,
sure.
yes.
Okay, just that something strange happened to Zoom, but never mind. So basically, EVM bin is like EVM, but wrapped into a binary. So you can run it standalone from OpenEthereum full node. Okay, I think we have jumped a bit. So going back to letter E. So executive state, we covered this. This is executive state, accounts DB. This is all like all together. Light. This is the Light client implementation, the so-called parity Light protocol. This is also an additional feature which is not a full node exactly. So if you would like to see it remain, I encourage you to visit us tomorrow, our weekly call, where we will discuss its future. Ethereum state machine. So this is the crate which contains the machine struct. And in the machine struct, what I found is that the most important part of it is the common params. So this common params, these are the parameters, which is basically the the hard fork configuration. So it contains a set of switches, a set of flags, which allow switching on or off the behavior of the chain, and it contains the various transitions at various block numbers here. So, for example, if this is not set, like it's set to an infinite block, like, or the block number, the maximum block number that is possible from the programmatic standpoint, then if it's EIP 145 transition, then these rules will never begin. So this EIP will never be activated. Or if it's some proper block number, then this EIP will be activated at that very block number. And we'll come to this, but this is all configurable in the JSON params. So if you want to run your own chain, if you want to activate your own set of EIPs at your own block numbers, then you can easily specify that in a JSON and load it at the OpenEthereum startup, and you will have your own chain. So, this is the machine, and also we have the ETH extensions here, but this is like an extension of the common params. So this is also a set of switches. Node filter. So node filter is something that I covered during the diagram, if you remember. So this is the smart contract-based node filter that allows us to manage permissions of network connection. And just to be super clear, what it means is the connection filter trait. This is not in the node filter crate, but basically it shows what the node filter can do. So it accepts a node ID of us, the connecting node ID, and the connection direction, if this connection is inbound or outbound. And the node filter will tell us if we can connect or if this connection should be rejected. And while this connection filter can be implemented as as a set of your own rules, not in the smart contract necessarily. In the node filter, it is a smart contract that you can deploy on your own network and use that for permission management. Pod. So this is the state account system expressed in plain old data. This is so this is the representation of the accounts without DB overlay cache, code hash, or anything like that. This is used in some places of OpenEthereum, like if I recall correctly, it is used in the mainnet chain specification, where the lists of the original of the seed accounts is stored. I may be wrong here, but I think it was that.
It's used for serialization as well, to serialize and deserialize accounts.
Yeah. So and this, yeah, but I just, okay, maybe I didn't find it when I looked
so it's
for
used
it.
in snapshots, for example, like when you warp sync and you dump the state of the chain to disk. That's what we pass through the pod accounts and pod state.
Right. Yeah, and yeah, it would make sense there too. So yeah. Private transactions. So these are private transactions feature. It is described in detail in the old wiki, so you can read how it operates there. So I'm not going to cover it, really. Then these are just the various resources, mainly JSONs, various JSONs like tests, for example, but also all the default chain specifications present. For example, foundation JSON contains the Ethereum mainnet specification, which is read by OpenEthereum by default, and according to which the execution engine, the state machine, is initialized. So, and yes, so we have like huge JSON here. Even VS Code warns me that, yeah, it's abridged in display. So yeah, you can read all the chain specifications if you want, and there are many as you can see, non-mainnet networks that we also support, which is one of the strongest things of OpenEthereum, is that it allows us to support just about any Ethereum-like blockchain, provided there is a JSON specification for it. Service. So this is the network client and network service creation and registration with the IO subsystem. So this is, so here we have private transaction service, and we also have client service. This is related to the internal actor system used by the OpenEthereum. So I think we should cover it if we cover the actor system properly, because like on its own, it doesn't make much sense to the outsider. So, but this is basically a glue to connect all parts of OpenEthereum to the internal messaging system. Snapshot. So this is the warp sync, or at least the part that is about taking and restoring snapshots of the blockchain. So in this case, we have like a set of traits, like snapshot service, so which handles restoration of snapshots to temporary databases and responding to queries for snapshot manifests in chunks. Then we have the rebuilder trait, which is about restoring from secondary snapshot chunks, snapshot components, about snapshot creation and restoration, and so on and so forth. But basically, the building blocks for the warp sync are here. Spec. This is the internal representation of the specs which are in the Rees folder. So they are loaded into ETH-JSON crate using ETH-JSON crate, and then transformed into internal representation in spec. And this internal representation, which is this is used throughout the code. But basically, it's the same JSON that we've seen before. So we have come to the core, to the ETH core crate itself, the ESRC folder. But basically, this is just the remains of its, so to say, former glory. So basically, some of the parts which just didn't go into other crates. So it's it's the client struct, which which contains the.
I mean, the client object is sort of like a God object in
yes.
OpenEthereum. It's way too big. You can see the minimap on the right there. That there's a lot of code in this file. Everything uses a client or a variant of it. There have been several attempts to slim it down. You will see when you go through the traits that there are, blockchain client, importing client, approving client. There are various subsets of client that is trying to extract important pieces of it so that you can pass around trait objects to it without having a full dependency on ETH core. There is a lot of work to be done here to clean up this code and make it more modular. But essentially, as of today, the client is everything. It's what ties every other crate together, essentially.
Yeah.
It does importing, it commits, it verifies, it, has references to engine, machine, and sync, and yeah, it all ties into it.
Also there are some other minor bits like database compaction profile, like one for SSD, one for HDD. The client config, which is a struct which just contains which aggregates all the configuration from all sources, like CLI flags, for example. Some of the traits which just didn't go into other ETH core crates. So so basically it's the client struct and some other small bits and pieces. State database. So this is the database, this is the state database abstraction. So it just manages the shared global state cache, and it is cloned throughout the code, throughout the code base, but there's always one canonical struct, canonical instance. Sink. So the sink is basically what contains the blockchain synchronization. So this is the strategy, blockchain downloader, blockchain synchronization implementation of Ethereum protocol, and so on and so forth. So basically, if we go inside, so we have we also have two nodes here. The primary code, this is the usual sink, and also the light sink. So I'm going to cover the main part here, which basically has the sink state, and it should be clear that there is the sink state when we are in the warp sink, and when we're not in the warp sink, basically. These are separate. So like the sink state is like pure information, but this is all meta. So the main part here is the chain sync API. So which is the thread safe wrapper for chain sync, which is here. And this is basically the sync handler, which just contains all of the sync state, which ties it all together. Like it contains the set of connected peers, peers active for the current sync round, the network identification, the fork filter, which is EIP2364. The snapshot downloader, and well, this is just the flag if the warp sync is enabled. So, and here, so this is also like a sort of a God object, but only for the sync. So this is what is directly started in the main chain sync, and is directly used from the very top of OpenEthereum client code. Trace. So this is what is used for transaction tracing, for TraceDB, basically. So the tracer trait used by executive to build traces. So it's this, like the VM tracer, and the special trait to access traces DB, like unified view for it. Try VM factories. So this is basically a collection of factories for VM and tries. And this is, well, this is what I showed you like some time ago, basically. This allows the creation of virtual machines. So the factory for the virtual machines, like create your own EVM with the schedule. And then we have types. So this is a very big crate called common types. This contains, as you can see, just types in the most just kind of shallow, I would say, sense, and that these are just these are not rich but poor objects. And I think some of the traits, but I may be wrong here. So things like transaction, for example, so the representation of transaction. So this crate doesn't contain any logic, but it contains the basic entities of which are necessary to us to operate on. Like header, like receipt, and so on and so forth. Verification. So these are the utilities for the block verification, and so in this case, yeah, so we have just a set of functions to check the blocks, and that's it. So just a set of freestanding functions. So we are leaving ETH-JSON now, ETH core. We are leaving ETH core, and we're going to ETH-JSON. So this is the deserialization of JSON specs, basically. So basically what it contains here in various modules, it contains various primitives from which are basically in each spec JSON. So just to be more clear, this is basically what each chain spec, JSON chain spec represents. So the struct spec, which has name, special fork name, engine, parameters, Genesis header, Genesis state, boot nodes, and hard-coded synchronization for the light client. And then various parts of engine, params, Genesis state, and hard-coded sync are all here.
Okay.
So basically it's this.
Okay, wait. We are bad.
Someone's talking with me, I think.
I think it's even because it's the only unmuted mic.
Can even mute themselves, please? Okay. So miner. So this is the OpenEthereum mining interface. So I haven't actually dug deep into this just yet, so I'm not like super sure what's in here. David, do you know like what we should cover in detail?
No, we should probably have a common code reading session about the mining stuff. I haven't opened these files either. I believe that it is handling the transaction pool and selecting which transaction go where and how to reprioritize the list, but that's me speculating. I know there are two pieces of it, one that is inside ETH core, probably because it needs a strong reference to the client. And I suspect that what we're seeing in the miner folder that is outside ETH core is the stuff that could be extracted. Yeah, I'm speculating.
Yeah, I guess we should cover or like you said,
I know this much that in a year and a half, I don't think we've ever seen any bug report that touched the miner code, which is often how one ends up knowing about this or that piece of code, right? Somebody comes complaining about something and you start digging in. And so it seems fairly stable. And
yeah, don't fix it if it's not broken, right?
Right.
Yeah, and I mean, you start feeling that tune when, especially when there are almost 200,000 lines of code to maintain. So you just tune off on some parts if they just work and don't touch them anymore. So parity. So this is the client itself. So this contains the main.rs, which is the entry point, and this is basically where the full nodes start. So this is like a very good point of exploration. So I'm going to cover this in a bit more detail. So we should remember that like the main arrest, like the main function, it might not be super interesting here, for the simple reason is that we have Windows, and on Windows we have parity updater, and this is like a wrapper, which is about auto updates and restart of the client because of auto update. Always, not just in OpenEthereum, but always makes things, the mains, a lot more complicated. So I'm going to skip the auto update right to, let me just see, execute impl. Right. So the execute impl, this is the real main of OpenEthereum. So this is parity/run.rs. So there is execute light impl. This is the light client execution, the light client main, but we are going to cover full node for now, and we have here run cmd, which is like a set of configuration, basically. The logger and like 2 callbacks, but we won't cover that in detail. So basically, here we have like the basic setup, like checking the configuration and loading configuration. Like migrations here in execute upgrades. Whether warp sync is turned on. And then we start creating the important entities. Basically, like account provider, spinning up the asynchronous runtime, the Tokyo event loop, creating the miner. So this is the creation of the client config. And then we start the client service here. So this is where the internal pipe this the set of internal pipes, the message bus is started. Then the
also generate is the snapshot object inside, I think. The client service. Yeah, it's just linking.
Yeah.
To.
Yeah. So it also So if we go into start, so we have the snapshot service is also here. So it is separate from sync, and it started here in the client service itself. So going back to the real main, we collect this set of hard forks here, and let me just, okay, so the node information store is here. Private transaction service also, and here we start the sync. So there's just a global factory which creates the sync modules for us, which is sync provider, manage network, and chain notify. Which are actually one and the same thing. Yes, they just implement three different traits, that is, for non-REST people, 3 different set of behaviors. So if we if the private transactions are enabled, we add we set the client service actor to be notified on the on the updates from the private transactions provider, and we also start the fetch. This we will cover it later on, but this is basically something that downloads data from the network, like the HTTP download, basically, not as opposed to P2P. Then we have the updater service, and then we start the RPC. So we'll cover RPC also later on, but basically this is about the JSON RPC interface, which can be used to access the client information via an HTTP, a WebSocket, or a Unix domain socket API using the JSON RPC standard. Then we have the secret store dependencies, the informant. Informant is the service that prints data out into the terminal. So when you launch OpenEthereum in the terminal, it will be the informant service that will print all the necessary information based on its own settings. So we save the user defaults, then set the handlers, and that's it. We have started the client. So we just return it, a handle, rather a handle to it. So this is basically the main guts of the main of the parity binary itself. But these are not all the libraries, but this is like the basic part. RPC. So this is, like I said, this is the set of JSON RPC servers which implement WebSocket interface, HTTP interface, and Unix domain socket interface as well. So it uses the JSON RPC crate, which is made by Parity Technologies. But yeah, it basically contains the set of traits here, which correspond to the Ethereum JSON RPC spec, which can be found on the old Parity Ethereum wiki. So it's this. You can see the name of the JSON RPC method here, and it automatically generates the the appropriate trait, which is implemented by the real implementation, like here, or yeah, so basically this. Scripts. So in scripts we have like a set of either scripts like bash scripts, or like a systemd service, an init script, a set of CI scripts, which are used by us to basically publish new releases, to build them and publish to various stores like Docker Hub, like Snap Store, and even like just pumping out a binary to GitHub. So this is all done here using the scripts in this folder. So this the updater is the Parity updater service, and so basically the updater service, what it does is that it reads a smart contract deployed in the network, and if that smart contract suddenly has a change, then a new binary is downloaded and the client is restarted. So this is something that on the one hand, which is like very, very centralized, and basically allows an oracle for every client that uses this updater service. But on the other hand, this allows for swift security updates, like in case sudden zero-day bug is found, updater, the fresh binary information in that contract may be changed by the developers, and then a new release is quickly pumped out to the clients that have this enabled. The future of this feature is also uncertain, so if you really want to see it stay, please join us tomorrow during the weekly dev call that we have. Util. So in util, we have various set of utilities which are used by OpenEthereum, but which are not necessarily tied to the larger code base, like ETHCore, for example, is tied. So it may even be sometimes used independently of OpenEthereum, but still it's geared towards it naturally. So Blooms and Blooms DB. This is implementation of the Blooms database, which basically allows us to quickly filter based on the Bloom ref. So it returns the indexes of all headers matching given Bloom in a specified range. So, and just to let everyone know, David is currently working on BloomsDB on some great improvements to it. So if you've had pain with it for some
Actually,
time,
no.
then it's not.
The BloomsDB is for traces.
Ah, right.
There are blooms all over the place, but essentially the traces database has one Bloom database, and that is what you're talking about now. And then there's a Bloom filter in the RocksDB database. And then there's another level of Bloom filters on the accounts level, and that is the one I'm working on.
Right.
It's confusing.
Yeah. So, but yeah, this is for traces, and it's used there. Dir is just a small set of utilities for working with directories, and this is the cross-platform set of utilities. So, like if you have Windows, then you'll have like one constant here, and if not, another constant. So, but yeah, just a set of small directory helpers. That's it. So this is EIP152, and this is just Blake2F compression function. So with the AVX2 implementation here. So a lot of math, but nothing too interesting, really. So this is EIP712. I'm not exactly sure what it does, because I'm not sure what EIP712 is about, but
it is a messaging protocol on inside Ethereum transactions, I believe. So what you have in here is essentially a parser, encoder, and decoder of these messages. Exactly why one would be sending messages back and forth is probably something Eduardo or Adria could know more about than I do.
Adria? Adria or Andrian? Oh, okay, never mind. Fake fetch. So fake fetch is basically the mock fetcher for testing. So it's only used in testing, so not very interesting for us here. Specialized version of HashMap with H256 keys. Also not very interesting. Fetch is a specialized fetching library exclusively for the use in OpenEthereum, like just fetching something from HTTP, and that's it. ETHCore IO is this is interesting. So for those who are knowledgeable in Rust, like I said, OpenEthereum uses its own actor framework, sort of an actor framework, and it is based directly on MIO. So the thing is that back in 2016, basically when OpenEthereum's development was started, back then, if you remember, it was called Parity Ethereum. So there was no Tokyo at that time, and there were no futures, no async IO as we know it. So the only thing at the time was MIO, and like the pretty handle to the asynchronous utilities of like Linux kernel, for example, and that's it. So Parity built on top of that. So this may look like very, very obscure, but this is how asynchronous messaging could be and was actually implemented before Tokyo arrived. So a bit of a warning, this code is very obscure, and it isn't the way that it would be built today in 2020, but it is what it is.
Yeah, I have seen in the code, also in some parts of the code, using futures also. So at some point there's some different things mixed.
I think there are only small portions in OpenEthereum that use futures, like maybe in the fetch part, and it actually uses Tokyo runtime inside, so not MIO but Tokyo. But like this is a very small part, and the client is built on top of this, of ETHCore IO. So
okay,
yeah,
it does use futures for everything that is RPC and
yes,
yeah,
yes, and RPC
and some other places as well. It shows up, but it's not pervasive. It's not 100% futures based.
Yeah, like you can basically turn off RPC and you can turn off fetch, but the main parts, like the core, like the sync, for example, and the dev P2P, which we will come to very soon, they are all based on ETHCore IO. So like the most important bits are not Tokyo. And the only reason why JSON RPC is not ETHCore IO but Tokyo is because it uses, I think it uses Hyper as far as I remember. So like, yeah, it had to be ported in order to be compatible with IPC and with HTTP Rust implementations, with transports themselves. So, but still, ETHCore IO is the base. So a HashDB is like managing short-term journal potentially containing many forks of mutually exclusive actions. So I'm not sure where it's used actually. David, do you know?
JournalDB is a very important for APC. The fact that it's hidden down in the utils should not be. It's actually kind of one of the core crates. It encapsulates the different modes of operation of the Ethereum client, such as when you run your node in archive mode or in FlatDB mode. This is sort of reconfigures the database in different ways, which is why you can't easily switch from running an archive node to a normal node, or a normal node to an archive node, or tracing node, or a fat database node. So it provides a bunch of abstractions on top of the tree, the core data structure of Ethereum, and that encapsulates these different modes of operation, and it also provides the overlay for handling reorgs. and the reorg handling code is pretty difficult to follow. But yeah, JournalDB is something that you will definitely want to take a look at if you want to look at the lower levels of the client operation.
Right.
So it's essentially where Ethereum meets the database.
Right. So I guess it deserves a separate code reading at some point then. So this is just KCheck 256 implementation of the hasher trait. Like the hasher trait is the this is in HashDB, so this is not related to the hash trait, which is in the Rust standard library, but this is for the HashDB. So I'm not sure where HashDB crate is used, to be honest. But
that's another one that is all over the place. It's also one of the core crates that is actually outside of the repository. It's in the TreeDB repository, which is still a part of the party organization.
Yeah.
As is the whole of the tree data structure itself. It's it is used to parameterize the tree.
Mm-hmm. Mm-hmm. Yeah, but so basically it's so we have a trait HashDB here, and hasher. So basically like a database which stores hashes and anything hashable.
That sounds about right. Yeah, where the keys are hashes. Exactly.
Yeah, yeah.
And it lets you abstract over what kind of hashes those are.
Yeah.
So that in the Ethereum project, they're KCheck 256, but other projects could use other kinds of hashing. And if you open up the Patricia Tree Ethereum crate further down, you'll see how the hasher is used as parameters to set up the types. So here you see that the tree layout implements the layout using the hasher that you sent in. It also defines how you encode your nodes. In the case of Ethereum, it's RLT with KCheck hashes for keys. But yeah, the hasher trait is it's part of what allows you to reconfigure your tree and your tree layout and your tree encoding.
Yeah. So this is atomically cached len for use with collections contained in parking lot mutex and rvlog. So so this is just to, I think, not lock the collection just to get its length, basically, like a wrapper to do this. That's it. Memory cache. This is an LRU cache which operates on memory used. So basically, a memory cache. That's it. RocksDB migration utilities are here. So, not going to cover this in great detail. ETH-core network. So in ETH-core network, what we have is just a small set of networking utilities. So the connection filter that I showed before, and entities like client capabilities, like client version, and parity client data. So which is basically the special network description of which is transmitted by the specifically by the OpenEthereum clients. So this is all for Dev P2P, which is the next grade. So this is the Dev P2P implementation of the ETH Core network library. So what it has here is basically the networking service, which is registered with the great actor system, the bus used by the OpenEthereum throughout. And the main point of entry here is the network service. And the network service, when it starts, well, it collects the, it gets the networking, takes the networking configuration. This is set in the OpenEthereum settings. This can be set in OpenEthereum settings, like, for example, the path to the configuration, the listening, the server listen address, the UDP port, what about NAT, the boot nodes, the number of peers. So all the networking configuration that you set via CLI flags and also we also can provide the connection filter. Remember the node filter, which filters based on the node ID. And we start the networking service. So what it does is basically the communication through using the Dev P2P networking protocol, which is described in, you can find in the GitHub Ethereum organization, the repo called Dev P2P, and it will be, it contains the description of the networking protocol, basically of how handshake between peers is done, how discovery of other peers is also done, and what connection message types are there, how they're handled, so how should the client behave, and so on and so forth. So basically, what I'm just going to cover is like the basic structures, the entities. So discovery. So discovery is basically the Kademlia DHT, finding nodes and like getting a list of what nodes to connect to. So discovery in OpenEthereum is discovery version 4. In our extension for it is underway, and discovery version 5. This is something that will be implemented in the future, but today it is discovery version 4. So, and discovery, like this is discovery new. So, and here we have host. This is the root IO handler. It manages protocol handlers, IO timers, network connections. So we have here the host information, which contains like our nodes metadata, like the key pair, like network configuration, a protocol version, the connection nonce, and info on our capabilities, so on. Contains the discovery, so it's initialized here. So everything. So how is this root IO handler initiated? Basically, if you remember, we store the key to the node key, the private node key, in a network configuration path, in the network configuration path. So it is loaded right here. So it's loaded or generated. Then we start the TCP socket, also start UDP. This is used for discovery. And then the root IO handler is up. So then there's also the code for initializing the public interface. So this is about universal plug and play. So punching through NAT. And as soon as we have initialized the public endpoint, then we start the discovery interface. And then we register everything with our IO actor system, so to say, to animate it, to make it alive. And basically, here we have action response. So as soon as we have something new coming into our socket, for example, some new packet, then one of these handlers is fired, and it reacts to the event. So, and that's it. So here we have the nodes, the node table. So this is the node table backed by disk file. So this is DHT as far as I remember. So the network service that we talked about. The notion of peer session over encrypted connection. And structure used to report various session events. So this is basically the dev P2P crate. So this is the custom panic hook. So when some part of OpenEthereum crashes for some reason, the panic goes up the stack and unwinds the stack, but at some point it stops, and it stops at this panic hook, which basically prints this message that this is a bug. Please report it at our bug tracker on GitHub. I believe we covered Patricia try with David before, so I'm just going to skip it. The registrar. So I'm not sure what registrar is, to be honest. David, do you know?
Isn't that how you register contracts on the chain that the client can or should be able to interact with, such as, you know, the pricing oracle? Possibly that is the only usage we have at the moment, but I could be completely wrong. I don't know. I have to be honest. It has something to do with interacting with contracts on chain, that's for sure.
Right. I guess it also needs a separate code reading, so. Yeah. So we're almost there. so the stats, just the statistical functions and helpers, like build a histogram, for example. Time utilities. This is about checked arithmetic. So basically, checked add for system time before checked add was added actually to the standard library. So there was no checked adding to the timestamp to forward it or to rewind it in the future or in the past. But it's still there. So it has been added to the standard library, but there is this implementation, and there are some reasons for it to still be there. But the pull request to remove all of this is currently up. So this is the try hash for try roots, but I think we basically covered all the try stuff before, like in Patricia try Ethereum, for example. So so this is just a small like a small display wrapper for error messages. That's it. And version, this is basically for like generating the metadata for to be included in the main to display the exact like the exact version with the channel name and so on and so forth. So that's it basically. So printing the version information. And I think we're done. So I think we have covered all the crates. So if you have any questions.
Well, yes, for me, like a general overview, it's super nice to have, to be honest. So I don't know which kind of questions I can ask. So, but I don't know if there are some parts of code that can be refactored without so much pain. I think that like maybe create names, some of them can be changed or just order it in another way just to improve that the code is more readable. And this kind of refactors with Rust are very painless. But I don't know if there are any other thing that could be done easily in terms of refactoring.
So your question is if like which parts are easy to refactor, or
it's like that people reviewing it is not getting into pain. Yeah, mainly.
like I mean some code can be refactored. Some is problematic. For example, like transitioning from the hand-rolled actor system to Tokyo, for example. This is yeah, this is not something that can be done in one day or 1 month or even 1 year. So this would be a very hard part, like really, because it would redesigning the whole architecture. Other things may be refactorable to make them better, but overall, like, we should remember that the client as a whole is more or less modular. For example, the bespoke engine trait, like, it's really simple in that you have the trait, you have the common set of behaviors, and you can easily implement your own engine for it, your own consensus engine. So it's pluggable, and it is the same thing in many parts. So it was not that good, I imagine, some time ago, but today it is good. It is modular, and individual parts can be replaced or refactored. So it's not that hard. But for example, the actor system and some other parts as well, they may be problematic.
Yeah, and for instance, it's like I see that some of the code, it's very, it's generic, that it's really okay. Like, I think the triads, you can you can use another kind of hash or something like this. So sometimes I am not about kind of abstractions that are not done. It just remove the kind of the if this code can be abstracted or not. I don't know if this could simplify the code in some point or not. So I don't know. For instance, it's like client has 3 threads or 4 threads. I don't know if this can be simplified or just doesn't make sense also. So it just tried to make a code that is more readable. It's like, I'm thinking like OpenSSL, that Google just got a copy and created boring SSL, I think. It's just removing the code that is not expected to be used in any way. It's not just removing models, it's just also removing some things that are not okay, that are just outdated. Yeah.
Well, again, some things that are outdated, they are outdated because their design is old, and factoring in the new design is not easy sometimes. So, like, some of the dependencies will be easy to operate, some are not. And like I said, there are parts of OpenEthereum which are not necessary actually today. Like, for example, the checked time utilities or the bespoke actor system, but you have to redesign code for them and retest it, and this may pose a problem.
Yeah.
So for the parts that have like long-term refactoring issues, what exactly is the roadmap? Like, is it like leave it until a major bug comes up and we have to fix it, or is there like an eventual plan for some sort of refactoring?
Okay, I think like the only problem with architecturally old parts like right now is that if you want to integrate an outside library, like an outside implementation of something into this, it is a problem. But if you don't have to integrate something, then it is not a problem and it works well. Like, for example, in case of the actual library, the internal message bus, The problem is if you wanted, for example, to fire a hyper HTTP request, that would be a problem because hyper is written for Tokyo, but not for ETHCore IO. So, but we don't do that. And even if we need to run a fetch, for example, then we have a fetch module which provides integration with hyper. So this is definitely not ideal. And definitely Hyper Tokyo would bring like much better performance. Not just Tokyo, but if it was Tokyo and this all internal messaging was written as futures assembled into tasks. But like, I don't think this is going to happen in the near future, definitely, and in long term, I don't know, because this would require a major rewrite of tens of thousands lines of code, which is like very sensitive to bugs and which will have to be retested. So, and it does not give enough returns to actually refactor. So as long as it works, and long as it does not pose any problem for implementing current EIPs, I don't think there is any reason to like really dig into it, as in not explore it and expand it, but actually rewrite it. It would really be a fool's errand.
Yeah, that makes sense. So the priority focus right now is just implementing EIPs and bug fixes.
Exactly.
Okay, makes sense.
Basically, OpenEthereum is good as it is right now. So there is a reason why it has a big market share. And performance-wise, I mean, it is optimized almost as well as it could be. And other than that, it is written in Rust, and Rust is great on its own. So this code is performant from the get-go. And we should just keep up with Ethereum development. And maybe at some point in the future, if we have to like really expand it, or we have to really change it, like maybe at some point dev P2P protocol, for example, I don't know if it will ever happen, but if it's replaced by lit P2P, for example, then we will need to actually not just touch, but rewrite the guts of the message bus, for example. And then will be the time when we actually do it. But otherwise, it doesn't make much sense for OpenEthereum to do any significant re-engineering. It just wouldn't bring the returns. It just wouldn't bring the returns to justify this.
Yeah, no, I agree. So just trying to change some important parts of the architecture now just doesn't make sense. So maybe it can be just scheduled at some point when we have more experience about internally how everything works and the kind of things, the kind of problems that just faces more in detail. But it's, I think, maybe this is after the Berlin Hartford for sure, if that makes sense. So I don't know.
Yeah, but yeah. So